it would be best generally if you select whatever motors from somebody that has engineers that can help you. And so typically the way the industry works is there are the sell direct to you, the consumer, and you found a cheap motor, and the burden is completely on you to make sure that you got it right. There's also a whole big part of industry which has manufacturers, and then they have high-tech distributors that have engineers that work there. In fact, we have tons of Chico State engineers that are application engineers at motor distributors. And they do this all day long, and their incentive to help you is because they make a little bit of money when you buy the equipment from them. So if you're doing design, you design using manufacturers, and either their websites or their app engineers at their distributor. And they have incentive to help you. There's lots of people that know this, if you shared your motor sizing, some of them will even do it for you. And they're fast, because that's the group right here. That's the group that does it all day long. You generally would like to, once you've designed that, but what I don't want you to do is no design from commodity distributors. This is kind of off subject a little bit, but we're right in the selection process. And by the commodity dealers are Granger, McMaster, right? However, because keep in mind the word commodity means you are responsible. It's all on you. You are responsible for getting the part right. As soon as you employ one of these other, or get one of these others to help you, you've got some help, and it's not all on you to do. So a commodity distributor, if you look through the McMaster parts catalog, there's a few specs that they list, and if you're going to go find a coupler, McMaster has tons of couplers. The one thing they don't really tell you is who made it. So when it comes time to buy it next time, they may have sourced it from somebody different. Maybe they didn't, but you don't know. If you design from the manufacturer and you have a manufacturer's part number, and you think that you're confident that it's right, then you can buy commodities. No design from commodity distributors. You buy commodities. Okay. From McMaster-Carr. That's fine. Buy your shafting, buy your 1/4-inch shafting, buy your O-rings, buy your C-clips, that kind of stuff. That's commodity stuff. Every engineer is kind of expected that they know how to do that. You can select it, and it works. As soon as you get up to motion control, find help until you're good at it. You need it.
Are customers like us able to buy products directly from manufacturers?
No, probably not. And you probably don't want to anyway, because more and more, all the engineers that are kind of helping customers get it right, they don't work at the manufacturers. The only ones that work, the app engineers that work at manufacturers, are ones that are working on high volume accounts. Everybody else is local. You would go find the local motion engineering distributor in the Bay Area or near your customer, wherever your customer is. And generally, they don't want to take direct orders. They will, some of them, but they know that every time that they take a direct order away from a distributor, they disincentivize the distributor from having engineers on their staff. And pretty soon there's like, yeah, we'll use somebody else's that doesn't go around and take the orders after we worked on them, right? So there's little subtleties like that that you have to think about. And it doesn't really matter for commodities that much, because commodities you can figure out. But as soon as you get to things that you can't necessarily figure out and you need additional resources, then when you're using those resources, you want to try and buy from those resources, right? Make sense?
Yeah, thanks.
Okay. So a little bit of non-technical stuff, but it ends up being kind of important. But just keep in mind, you want to, you need a manufacturer's part number. It's very helpful because you're designing, you guys are engineers, you're designing in parts into a machine. The McMaster part number doesn't carry through when you need to buy it 15 years from now. And hopefully your machines that you're making are not just one-year machines. You've got to think, hey, this machine's going to have a life. It's going to make this particular product for 5, 10, 15 years. Manufacturers are really good at making sure that if they replace something, here's the replacement part. The commodity distributor doesn't care. There's no, unless they downloaded it from the manufacturer, it's just not their thing. Oh, you need a coupler? Well, here's what we got today. So, okay. How are we doing on time? Yeah, we're fine. So, if you determine the peak torque, I'm on to step 6 now of finishing up this robotic. We've talked about our little safety margins. Then step 7. Step 7, we get to check the load to motor inertia ratio. So I need to deal a little bit with inertia ratios. Okay. So one of the things that happens, because your components have 2 things, lost motion, meaning like backlash, or wind up or deflection, and you only really get to tell the motor what to do, and it has a series of mechanisms between that and the actual load that you want to move. When you put in load profiles for your motor sizing, it's really an ideal load motion, and it doesn't deal with that there's going to be actually a harmonic, there's going to be a transfer function in between those. So since you don't have a transfer function for this thing, and it's not worth doing because you're only making one of them, and it's not a research project right now, don't make it one. Just do the calculations. There is one other thing that happens if you have a large mass, large rotary load. Let's say that you had this system. Let's say you had this large, and we'll say that's steel. And we're going to say this is, I don't know, 660 centimeters. Okay. And then you say, well, I have this big rotary mass that I need to turn. It's turning in air. Let's attach a motor to it, and somehow we'll run the shaft up through here, something like that. I don't know. You attach it. You maybe put a nut on the end of it. You're turning it on the shaft. This motor shaft, it's about a 1/4 inch motor shaft. Right, and we talked about this. A 1/4, when you deal with the deflection, you grab the motor shaft, it feels real stiff. But as you know, a 1/4 inch rod has some torsion. The problem is when you do your motion profile, you are calculating what this does. But when you finally set up your system, you only get to tell that what to do. And so since you tell that what to do, what's in between these two is harmonics. And this doesn't even have lost motion. This is direct drive. So what happens is if you start this out and you have enough torque to move it, if you could somehow get rid of all deflection and you had enough torque to move this load, it would work. But as soon as you add a little bit of spring in between, think of this right here as a torsional spring. And as soon as you add a spring in between two, I'll draw it a linear version of the same thing. Let's say you have this mass here, and then you have a spring, and then maybe you have a big spring, and then you have another little spring. And finally over here, you have mass of the load, and maybe you've got some friction on it. So really what you want to move is that, but what you get to control is that. You see the problem. At some point, if this is much larger and you have an unstiff system, this is going to be doing whatever it pleases. Once you put energy into the system, it's going to be doing whatever you please. This could be over here moving back and forth, your exact predictable motion profile, point A to point B, point A to point B. But this over here is doing whatever it pleases. And you can actually have one moving, you can imagine if you've ever hung a mass from a spring and tried to, lift the spring and had the mass go up and down. There's times when if I was just going ding, 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 ding up with the hand and trying to get the mass to do exactly the same thing, the only way that mass is going to do the same thing is if I weld it together. Now they move together. As soon as you add a spring in between, this does something different. That's the problem. How do you know if it's going to be a problem? Where, as you design along, where do you go to look up the stiffness of the gears, the gear teeth? Where do you go to look up the stiff? Well, the coupler actually has a stiffness. The point is, I guess, as you go along in designing your machine, a lot of that stuff you can't really look up very easily. So you start to get a gut feel for if you're using stiff components or not stiff components. I see, for instance, a common thing people do when they mount a motor is they'll mount the motor and they'll say, you know what, let's make a motor mount here. And there's the motor mount. And so we mount the motor up to this, and they make this out of 1/8 inch steel. You could almost grab that motor and bend it with this 1/8 inch steel. It's your whole motor mount is not very stiff in that direction. Maybe that doesn't matter. Maybe what only matters is in the rotary direction. But the point is, since you have somewhat of an unknown stiffness with these 6 different components that you've built into your system between the load and the motor, it's worthwhile to look at the inertia of the load compared to the inertia of the motor. If you have a high stiffness system, if they're welded together, we don't care what the ratio is, because the load will do exactly the same as the motor. But as soon as you have mechanisms in there, it does something else. And our goal is to have this do the motion profile and not completely dominate the motor. So there's lots of people that will give you inertia ratios. The manufacturers of motors, this is funny, the manufacturer of the motor, you know what they like? They like a 1-to-1 inertia ratio. Oh, ideally, you should have a motor the same size as the load, which guess what that makes? The motor, your load's not going to change. So what happens to the motor? It gets big. When the motor gets big, it gets expensive, meaning you're buying big motors. Manufacturers like that. No, very seldom do you need 1-to-1. If it's greater than, 10-to-1, be concerned. That starts to mean that the load is going to win if there's any sort of deflection in there. It's not going to work. So greater than 10-to-1, no, probably not. So typically you're aiming for, and you have control over this in what you design and the inertias of what you design, and also you have control over this with the gear ratios that you choose. And so as you choose that gear ratio, the inertia, if we put in a gear ratio between right here, if we put in, let me undo that. If we put in a gear ratio right here, N, all of a sudden, if this, let's say that you had something that this was 100 and this was 1. You had a 100-to-1 ratio, and you put in a gear ratio of 5. Let's say n is equal to 5. If n is equal to 5, then all of a sudden, this 100 gets reduced by 5 squared. So by putting a 5-to-1 gear ratio in there, you not only make the speed and the torque, you've turned your motor from a high speed, low torque device to having more torque at lower speed at the output. Oops, I lost some stuff. At the output of the gear head, but also 100 divided by 25, you're now down to, now you've got 4-to-1 ratio instead of 100-to-1. Oh, this load is still big, but to the motor, so what we're really not dealing with is absolute values of the things. It's how big does that inertia look to the motor, not just how big is it. That make sense? So when you add gearing, it makes that look much, much smaller. So far, we've dealt with peak torque, or worst case torque. And one of the things that when you deal with some kinds of motor technology that have the ability to vary the amount of current in different parts of the profile, then you can't just look at worst case. You also have to look and make sure that the motor's not overheating. I'll give you an example. If you're dealing with a stepper motor, so if we look at the speed torque curve for torque versus speed for a stepper, I drew this last time. It has, you know, a couple different sections to it. A constant torque region, constant torque, and then a constant power region where the torque changes, constant power, where the torque trades off for velocity. And since torque times speed is power, you end up with the constant power region. A stepper motor, this is a 100% duty cycle curve. Meaning when you power up the motor, but you give it a certain amount of current, and it takes that amount of current the whole time. Whether it's moving or not moving, the windings are energized and it's holding a position, because the idea is it's a positioning device primarily, not a torque device. So this is, for instance, a stepper motor would be a bad choice for a mobile vehicle, because if you're just sitting there to stop, you may need some sort of holding torque, but generally you don't want it to be using maximum current the whole time, or your battery's going to go dead. When you go to a servo curve, then all of a sudden you're going to get two lines. You're going to get a peak line, and you're going to get a continuous. So the continuous line, that's the same as that. That's apples to apples, continuous to continuous, and that's usually the best way to compare different components anyway, is to have continuous torque to continuous torque, 100% to 100%, no asterisks in there. However, the one thing with a servo is that you're allowed to operate up in this region for some period of time, 2 seconds, 5 seconds. Whoever made the curve and published the curve decided on how long you can maintain in peak. They may have even said, oh, here is peak, and this line up here is good for, this, the asterisk on that is that's good for 0.2 seconds without the motor overheating, because the heat in a motor, essentially a motor is three things that you have to think about when you're dealing with the motor. A motor is a heater, and that's because of I squared R. You're passing current through the motor. It creates heat is power. It is a inductor. An inductor means that you have a rise time in current. In other words, when you first apply the current to the winding, it doesn't immediately make torque. It has to charge the inductor. So we got I squared R from the resistance, inductor, and one other thing. Yeah, anyway, I'll come back to that. So on our when we're selecting the peak, in order to find out what peak torque you need, you're going to look at your worst case torque and make sure that you have enough worst case torque so that that torque value that you had, if it was here, you'd be looking at for that particular time period, maybe hopefully it's less than 2 seconds, you can go into peak. But at some point, you have to look at the overall amount, and you can't stay in this area for too long. So you have to look at the RMS torque. And the torque RMS calculation is kind of ugly, and it's not fun, especially in a motion profile that has 7 segments to it, because each one of them have a different amount of motor heating that happens. So the RMS torque, you're really looking at the square root of, and it's a huge term, and it's torque in the first segment squared times the time of that segment, plus torque in segment 2 of the motion profile times time 2, right? Dot, 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 out here to torque during the rest period, 7 times how long you rest, 7. And then down in the denominator, I don't know if you guys, you might not have actually done this calculation for anything particular. You just heard about it. But what down in the bottom is T1 plus T2 plus T3, and T7, this last one, that one, the rest is where your motor cools off. So it turns out that that's the real important one in the RMS, is that you have time to rest, and that drops your overall value down. So when you look at a closed loop system, you actually look at the peak and look for a safety factor there. Then you go look at the RMS, and you're looking for a much less of a safety factor, because really all you're doing is making sure the motor doesn't overheat. And that's dependent on ambient temperature. It's dependent on how you mounted the motor. Did you mount a heat sink to the front of the motor? It's dependent on, is there cooling of any other type around it? So there's, it's kind of hard to exactly pick and say, but so the RMS, you tend to look for maybe a 20% safety margin instead of 100%. Much, much less. The peak torque, though, that's your real safety factor that you need to deal with. So you got to deal with RMS torque. And then the last thing that you've got to look at, when you have a motion profile and you are accelerating, then you're going for some period of time, the one other thing that you have to think about is regenerative energy. Motors don't really care which way the energy is flowing through them, if they're being motors and they're creating torque, or if they're getting spun by the load and they're turning into generators. And if they turn into generators, then the whole idea that you typically have of pulling current out of the wall, putting it through the power supply, and driving the motor is wrong, because now all of a sudden the load is driving the motor and it's generating power. And so you have to start thinking about where does it go? And it's a whole different conversation to have. But the main thing I want to do is have you at least think about during this segment, for instance, let's say you had a mass that was going from point A here, we'll call it point A, point B, C, and then D. And we're going vertical with this. So as this mass moves from point A, so this might be point A, B, C, and D in our motion profile. So the ideal is at some point it gets raised up to this level here. Well, in this motion profile, you can pretty much know, you can sense this, that you're putting energy into this mass to get it from here to here. You added potential energy. Kinetic energy started out at 0, grew to maximum at this point here. There's maximum kinetic energy because that's max, mass is the same and velocities is now at its max. Same here, but it's gained potential energy. And so when you stop at D, it's got potential and kinetic energy. So what happens when you do this? You rest for a little bit, and then you do this profile. You move backward. You go the other way, essentially. Remember, this is speed, and this is time along here. So now you're just going to go backwards. You're going to go back and take this mass, and we're going to move it, back down. First we moved it up, and now we're going to move it down. Well, as you move it down, at the top, it has maximum energy. How much does it have when it gets back there? How much energy does it have? 0, right? It's not got velocity, and it's back down at its base level. So here it had max, here it has 0. Where did it go? Right, so some of it goes to heat, and the rest of it has to be put back into a capacitor, back into something, burned across a resistor. You got to deal with it somehow. If it's a little mass, probably just the internal resistance of the windings and heating up the motor probably is got what you want. But regen typically would be the worst from here to here. In this section, which is right here, that particular point of the motion profile, it has 0 at the end, and it's got some kinetic and it's losing potential. You may have something to look at in that section. And that's essentially total energy calculation. That's back to your, kinetic, you remember this, plus potential at each segment. And that's in joules, right? And you're really looking at power in joules per second. So you kind of need to look at the amount of time that you're losing that energy over to decide to make some decisions. Something to think about if you have and the triggers are a huge inertia will have lots of mass, and so it would have lots of kinetic energy and potential energy. Vertical systems have to deal with that. Those are kind of your two main triggers, I would say, is one of those.